Hello Year 12. Today we're going to be learning about the shapes of covalent molecules. In order to be able to access this video, you need to make sure you're confident with drawing dot and cross diagrams for covalently bonded molecules. Have a little look over your notes from GCSE, and when you're feeling more comfortable on it, come back to the video if you're not feeling comfortable at the moment. Okay, so these are the specification points we're covering. You'll notice there are a few molecules listed in the specification that you need to know about. I'm going to cover all of those today. At the end of the video, maybe pop back over to this slide and check that you understood all of these molecules that are listed and that you could write the shape for all of these. Draw the shape. Okay, so how do we work out the shape that a molecule occupies in space? Well, the thing we use is something called VSEPR, which stands for valence shell electron pair repulsion. Now, what does that actually mean? Well, the valence shell is the bonding shell, the outer shell. You'll notice we've gone back to using the shell approximation of an atom here, because it works pretty well for describing the shapes of atoms and working out where things are. So the valence shell are all of the electrons in the outer shell. An electron pair, a valence shell electron pair, is one of the pairs of bonding electrons on the central atom. So here, the central atom is the aluminium atom in this aluminium trichloride molecule, and the valence shell electron pairs are these pairs of bonding electrons. So one aluminium electron, one chlorine electron. And because they're electrons and they're negatively charged, they will repel each other. There are two rules that govern how the shapes work. If you follow those rules, it should be very simple to work out the shape of a molecule. First rule is that electron pairs will always try to be as far away as possible. So for this molecule, it's quite simple to work out what shape that will be. There's only one way they can organise themselves in space, and that is as a triangle, essentially, with each bond 120 degrees apart. You will be expected to be able to write on the angle when you're answering questions on this. Some of this will be a case of just remembering it, but for this one it's quite easy to work out. Okay, now this shape is called trigonal planar. So let's look at some more. We're now going to whiz through a load of different atomic shapes. So let's look at beryllium chloride. Beryllium chloride is one example of this shape. There are many other compounds that do it. So beryllium's got 2 electrons, chlorine needs 1 more. We form 2 covalent bonds to beryllium. We've got 2 bonding pairs, and you'll notice there are no lone pairs on the beryllium. There's loads on the chlorine, but none on the beryllium, and that's the one that actually counts. So we have 2 valence shell electron pairs. They repel each other to be 180 degrees apart. This shape is called linear. Next one we're going to look at methane, a bit more interesting now. So we've got 4 electrons which form 4 bonds. 4 electrons in carbon shell form 4 bonds. So there's 4 valence shell electron pairs, all bonding pairs. They repel each other to form a tetrahedron. So this shape's called tetrahedral, and the bond angle is 109.5. Okay, what about if we have 5 valence shell electron pairs? We're breaking the octet now. So we're using the d orbitals on phosphorus to go bigger than the octet. And for this one, there's actually 2 angles. This is a quite common mistake that people make in exams. They forget that there's 120 degrees here and 90 degrees here. They are 2 different angles. It's called trigonal bipyramidal because you can think of it as having 2 trigonal pyramids stuck together. So we have 90 degrees between the these are called axial bonds. You don't need to know that, but I think it's quite easy to think of them as that. They're kind of like an axle through the molecule. So these are called axial bonds. 90 degrees between them and these, which ones are like through the middle, so they're the equatorial bonds, like the equator. They're 90 degrees to each other, and there's 120 through the middle. So it's a bit like a trigonal planar molecule with 2 more fluorines stuck on top. Okay. So it's got 5 bonding pairs. Finally, for completeness, let's look at 6 bonding pairs, which we need to go up to. We have 6 bonding pairs around the sulfur, and that forms an octahedral shape. This is an octahedron. If you were to fill in the gaps, it would be an octahedron. And there's 90 degrees bonding. The bonds are all at 90 degrees to each other. Okay, so rule number 2. Lone pairs repel more than bonding pairs. So that means we count them as a pair when we're working out the shape, but then we squash the bonding pairs together a little bit more. And most importantly, when we're naming the shape, we don't actually include the lone pairs in this name. Let's show what I mean on that on ammonia. So we've got 4 electrons in nitrogen's outer shell. It can't break the octet because it doesn't have any d orbitals. There are no 2d orbitals. So what happens is nitrogen forms 3 bonds with hydrogens to fill up its outer shell to get 8 electrons. So we've got 3 bonding pairs. We've got 1 lone pair left over. So this would be, as we've got 4 pairs in total, we're going to have a tetrahedron. So that would look like this. We can think of this bit sticking up as the lone pair, and these 2 bits as the other pairs, the bonding pairs. But this lone pair is going to repel more than the others, which squashes the shape down. So the angle is actually 107. We call this shape pyramidal. Notice we now don't have the lone pair sticking up. At this point, I probably should introduce something I should have introduced a little while ago, and that's what this notation is. You'll notice in all these drawings that some of the lines are drawn just as normal lines, some of them are drawn as wedges, and some of them are drawn as dashed lines. So the idea is, so that you can represent a 3D structure, you have a dashed line to represent a bond that is going into your page, or screen in this case, and a wedged line, like this one, represents a bond coming out of the page. So you can think of it as being a bit like a perspective kind of thing, like it's going into the page. And then the lines that are just normal lines, they are in the plane of the page. They are not going out or into the page. So that's how we add a little bit of 3-dimensionalness to our drawings. So look back over the drawings you've done and make sure the wedges and dashes are in the right places. Okay, what about water? So in water we have 2 lone pairs and 2 bonding pairs. So we're going to have a shape based on a tetrahedron again, but we're going to have a lot of repulsions. Lone pairs repel lone pairs a lot. They repel bonding pairs quite a bit. Bonding pairs repel each other the least. So the shape we're going to end up with is going to be even more squashed than the bond angles in ammonia. So we're going to have 104.5 degree bond angles. Sometimes it's called angular, but I think for your exams we'll call it bent or bent line. Sometimes it's called linear as well. Non-linear, sorry. Non-linear, bent, or angular are all perfectly fine. You'll notice they've still left the wedge line on here to show that this was originally coming out of the page, this bond. Okay, so what I'd suggest you do now is go back to the specification points, look at the molecules you need to be able to draw the structure of for your exams, and make sure you can do that. In the lesson on Monday, we're going to be going through this a lot more thoroughly and looking at how you draw some more complicated molecules. Thanks for watching.